Okay, the next speaker is Finn Larsen. He's going to tell us about an attractor mechanism for NADS2 and CFT1 holography.
So thank you, Kostas, and thanks to Johanna and other organizers for putting together such a lovely conference and giving me the opportunity to speak. This is, in fact, my title. It's not the one that is announced. There's a key thing here that is not a typo. This is the actual title. It's incredibly clever, but this is the second time I give the talk, and it's the second time that it has been announced with the wrong title. Anyway, let me start. This is a talk about ADS2. Why are we interested in ADS2? Well, extremal black holes, they're important to us when we try to understand black holes. The extremal black holes, of course, are the black holes with the smallest mass within a given charge sector, so we can think about them as ground states. That's some kind of quantum gravity theory. If you go and construct such things, then, for example, in my simplest cases that I'm going to have in mind are going to be simply spherically symmetric black holes in 4 dimensions, the simplest thing I can think of. They have been known for a long, long time that they have an ADS2 cross S2 near-horizon geometry, that Toddy-Robinson is called. And in fact, it has been developed now that all extremal black holes include an ADS2 factor. There's a theorem to that effect. So all told, we're interested in ADS2 quantum gravity, and that's because it describes some key features of black holes. Now, so why don't we just go and do holography? Because we learn in ADS-CFT correspondence that once we have an ADS, we should go and find a CFT. Well, that has turned out to be not so clear how to do that in the case of ADS2. There's been a lot of efforts, but they always seem to have some issues with them. One of the issues that come up is that there are no finite energy excitations in ADS2, that if you try to put in something in ADS2 that actually has energy, it will break your ADS2 asymptotic boundary conditions, and that means you thought you had an ADS2, but you actually don't have an ADS2. So what do you do now? How should you think about this? There are many other related unpleasantries that somehow are related to each other. And the upshot is that ADS2 holography is just not well understood yet. So it's something that's interesting to do. Well, a recent approach that has been very popular is to basically take the hint and saying, well, so if you put some stuff in the ADS2, you're going to deform it, you're saying. Well, why don't we just learn living with that? And instead of actually considering ADS2 and CFT1, we do something that really is deformed. It is nearly ADS2, and it's going to be dual to something that is nearly a CFT1. Well, what you have to live with then is that your ADS2, which looked like it had an actual nice conformal symmetry, well, now you have a broken conformal symmetry because it's not an ADS2, it's nearly an ADS2. And it's broken actually in 2 different ways. One, by the boundary conditions that when we get far away, it isn't really ADS2, it's only nearly ADS2. And also it's broken in an interesting dynamical way. There's an anomaly in the system. So there are interesting NCFT1s that have realized this. The SYK model, beautifully reviewed just a couple of days ago, has led the activity in this area. What I'm going to do is not at all looking at the field theory side. I'm exclusively going to consider gravitational aspects. And well, this is late in the conference, so I'm actually going to be exceptionally simple. I'm going to focus on just a single aspect, really, of ADS2 holography. And I'm going to do it in the simplest setting. I'm going to consider these aforementioned extreme, nearly extreme 4D black holes that have spherical symmetry, they're asymptotically flat, they're the kind of solutions that people learn about in their basic GR course. Well, to be a little bit more precise, the setting I have in mind is the following. I look at 4D supergravity, so I make it a little bit stringy, but just at the supergravity level, it's really just gravity, it's ungauged supergravity, and then I add a bunch of n=2 vector multiplets. So in this context, we have not just our standard Rystrom-Nordstrom black hole, we have things that are a little bit more general. In general, we have a mass for these black holes. Since we have a whole bunch of vector multiplets, we have an electric and magnetic charge for each of these vector multiplets in general. And since we have n=2 vector multiplets, each time you have a vector, except for the one vector that's dual, that's in the multiplet of the graviton, For each of the other vectors, you also have a partner that's a scalar, that's a complex scalar. So in this context, we have a bunch of vector fields and we have a bunch of complex scalars. This has been a very instructive system to analyze in the case of extremal black holes. It's been studied a lot, and I'm going to try to generalize some of that study to the nearly extreme black holes. So, that's a reasonable thing to do. So what did we learn for the extremal black holes? Well, a key thing that we learned is what is called the attractor mechanism. You should think about the solution as being a flow. The scalar fields, they are something at infinity, which are boundary conditions. They are put in by you. And then you solve your equations, and that means that your scalar fields, they will move as you go radially in, and they will become something at the horizon. The interesting thing is that this something is given by an attractor mechanism. No matter what your boundary condition was out of infinity, what you actually started with these fields with, what you will is that you will always end up with the same thing, something that depends only on the charges of the black hole. It does not depend on what your scalar field value was. So that's what the attractor mechanism is. And it's an absolutely essentialized space of theories, but I don't really. And since this is independent now of the scalar values, one of the scalars is even the coupling constant. That's how we introduce coupling constants in string theory. It's a Vev or some dilaton or some such thing. And since the theory at the horizon doesn't depend on that Vev, that means that it's independent of coupling, and that's why we can study extremal black holes in great detail. So this attractor mechanism has been incredibly fruitful. I've described here just the very basic supergravity, n equal 2 supergravity mechanism in the spherical case, but it's been also very fruitful to generalize this to all sorts of other situations, rotation, gauge supergravity, extended black holes, higher derivatives, big industry, and a lot of fruitful lessons in that direction. But I will not at all talk about those things. I will just stay, for pedagogical reasons in this talk, to just the spherically symmetric case, even though there are generalizations to at least some of these different things. The generalization I want to do for now is just saying, well, this is what we learned about the extremal black holes. What can we do for the nearly extremal black holes? Because, we're now in a slightly different situation, but it shouldn't be that different. So what does the attractor mechanism teach me? Well, one thing to realize is that there's a near in the nearly extremal black holes actually appears in two different ways. So just from, it's really essential that there are two different ways. Well, the way we think about it is that the extremal black hole has the minimal mass in a given charge sector. Well, that's good. Now that we go nearly that means that it has not quite the minimum. In other words, we have a little bit more mass. That's one thing that, one aspect of the nearly ADS solution that we're interested in, is that it's not really ADS. And from the point of view of the scalars, well, since the horizon is no longer exactly extremal, they don't quite get to their extremal value. But there's another aspect too, which is that we don't consider just the horizon. We consider the near horizon. So we actually consider a little bit more of a region here. So therefore, it's also nearly ADS or nearly extreme black holes in the sense that we don't consider just the horizon region. We consider nearly the horizon region. So there are two aspects here, and we need to deal with both of them. One of them is that the scalars don't really go to become constants. And the other is that even to the extent they do, they're actually varying as part of space because they haven't made it all the way to the horizon. So this breaking pattern will introduce new scales, and these scales are interesting. They're fundamental for this N-ADS2, N-CFT1 holography. It's important to know what these scales are and to compute them and study them in different examples, because now we are in a situation where we do not have scale invariance. Since we don't have scale invariance, we should ask, oh, what are the scales? So that's sort of part of the picture here. So one of the important scales that certainly have come up in many of the original studies is the specific heat. So let's think about the entropy of these things. If you're in the strictly extremal case, what's the entropy? Well, the entropy you might compute as the area. My L2 here is the length scale I have of my sphere, so 4 pi length squared is my size of my sphere divided by 4g. That's how I get my area law entropy in the simplest case, like here. Well, this I could think about as actually being a reduction from 4 dimensions down to 2, and the way you get that reduction down is that you multiply the volume here by this, 1 over g4, and you say, actually, this is really like 1 over the 2-dimensional coupling constant, which is a constant, and it really doesn't have dimensions. This is what we mean by saying that the extremal theory doesn't have any length scale. It has a large number. That large number is the ground state entropy, but it's a dimensionless number. The L2, the length that it looked like you have, actually sort of disappears from everything. You only have numbers. Now, of course, we are not in the extremal case. We are in the nearly extremal case. So in the nearly extremal case, the entropy is, well, different. It's not just the extremal entropy, it's a little bit above. And since we add a little bit of entropy, entropy is basically heat. So therefore, the leading coefficient here, we can think about it as the specific heat. I like to think about it instead as really just being a length scale. Some people say it's the inverse mass gap. These are all equivalent characterizations. This C here has a dimension, and that's the important part. It's a length. So what is that length? Let's go and look at examples. In fact, there's a literature has sprung up on this, and they all seem to find that actually the length scale seems to be pretty much this. I got my L2 back. I got my length back. This seemed to appear in a lot of different papers. Some people have said maybe this is universal. That's clearly not correct, but some people have said that, so therefore it's worthy of saying that they're obviously not serious. And I will compute it in a bunch of cases and see that obviously this length scale is not universal. So this was just an aside for motivating one of the aspects of looking at these scales was to say, well, they can't be universal, can it? No, it can't. So go and compute in a bunch of cases, some of the people have done that have suggested this. They've done the classical physics thing of saying, well, once you have two examples, both of which give something, surely it's generally true. Well, try three. So the preview of where I'm heading for my attractor mechanism, my near attractor, is that yes, we are introducing a lot of scales. What do these scales depend on? Well, they depend on the parameters of the black hole. The black hole has charges. P and Q, electromagnetic charges for my fields. It has scalar fields. These scalar fields have some value at infinity, part of my boundary conditions. And what happens in my flow when I get really near the horizon, but not quite there, is that there will be some scales, and those scales will depend on these different things. So you say, okay, well, so that means I have a lot of parameters, and that means I've lost my attractor mechanism because things are complicated. Well, what is really nice is that it turns out that they are not actually complicated. It turns out that if you have understood and studied the extremal attractor mechanism, and already many people have done this, then with only a teeny little bit of extra work, I'll show to you how to find all these scales. So you already did the work. I just need to harvest that work and interpret it and say, well, you did a little bit more actually, maybe than you even thought you did by the stuff you already did, just at the extremal attractor. There'll be no need, for example, to simply construct these flows and study the flows or do actual solution of non-extremal Einstein equations, which is hard because, they're difficult to find non-extremal black holes. But since we are near the extremality, enough simplifications that come from the extremal things actually will carry over that we can easily do the computations that are needed. So that's nice. Well, let me first deal with the non-extremal part. So I'm not even near extreme right now. I'm saying, well, look, we need to go away from extremality. What happens? Well, what happens, at least in this class of theories, n=2 theories, is that I can give you a relatively simple, very simple form of what the solutions are going to look like. They depend, importantly, on a radial function here. This is the thing that multiplies the sphere, so it really is the radius of the sphere. But importantly, the radius of the sphere obviously changes. It's something at the horizon, and then it gets bigger and bigger and bigger as we go out. And then there are these functions here. This radial function appears everywhere, but importantly, there's also this little stuff here. You'll see that the little m is something that's a mass-like parameter. It historically actually came from that this was the Schwarzschild mass in a special case, but I think about it as just a parameter that obviously has dimension length, and the important thing is that there's a horizon when r is equal to 2m. And therefore I can go and study now this black hole without actually knowing what this radial function is. It's easy for me to do things like computing the entropy. What do? Well, I compute the area of the circle at the place where I have a horizon, so that's good. I have a formula here for my entropy. That's the one that I'm ultimately going to be interested in. And I can look at the Euclidean section of the time, and I can check that when is there no conical singularity? That gives me a function for the temperature that looks like this. And I also see that, oh yeah, that little m here clearly is something that is, when it's small, or especially when it goes to 0, I get my extremal limit. And that makes sense because then I get a double pole here. And once I get a double pole, that really is the hallmark of me having gotten to an extremal black hole. And it's a good thing to check here that, yeah, that makes sense. And it also persuades me, and I can do a bit more work here, to show that this function r squared, one important thing with this parametration I've done here is that this r squared function is actually a regular function in the near horizon region. That's why I've shifted my coordinates the way I want it. It's not like, for example, this double pole is being partially canceled by this one being linear in r, or this one being itself something that has poles in r, or anything like that. It's just a nice function. Of course, we can write it down in many cases explicitly, but that's not my point. My point is that it's some function, and if I just knew that function, for example, by solving the actual Einstein equations in the non-extremal case, I would simply have the solution. And then, knowing that, what I should do is to take the extremal limit, and I should take the extremal limit with all the charges and moduli fixed. So I haven't written actually what the matter fields are, but I should obviously also find out what those are. Now, an important thing to remember here, though, is that even though I have written this radial function as something that depends on r, well, of course it depends on r, but it actually also depends on the mass, because obviously the function depends on which black hole are you considering. So it has a bunch of parameters here, mass, charges, and such things that are kind of suppressed. So this function has those things and depends on what these things are. On the other hand, I have another function that's sort of similar to r, which is the entropy. That depends on the mass. We think about this r, the radial function, as being the thing that computes the area. So obviously it sort of gives the entropies related, but it's not the same. This one actually depends on two parameters, the mass and the position. This one, the entropy, depends only on the position, only on the mass. This means I can play now. I can try to say, well, what happens when I go nearly extreme? Well, remember what I do is that I do two different things at the same time. I have the mass being not quite the extremal mass, or go a little bit above. And that means that my change in entropy is going to be this when I go a little bit above. On the other hand, I could also try to compute my entropy by saying, well, it's 4 pi r squared is the area. Except where should I compute it? Well, now I have two changes. My r squared function dependent on what is the mass. And, of course, the position of the horizon has changed. So I do two changes. The great simplification that comes is that the change in the mass here is actually of second order in the temperature. The change in temperature, change in entropy is linear in temperature when I go above. This thing here is 1 over temperature, so this change in mass is square of temperature. Well, fine. This is very well known. Other people have pointed it out. What I point out is that that means that this function here, this is regular, is multiplied by t squared. This means that this term is not important. That's really nice, because that means that one aspect of being near is going to be addressed here. I can actually use that r squared function, the radial function, of the extremal case, and then just use the fact that that r squared should be computed now somewhere else. So my entropy of the near extremal black hole I can actually get by taking the radial function of the extremal case and evaluate that, but just not at the horizon of the extremal case. I have to evaluate it somewhere else in order to take into account that it's nearly extremal after all. So this way I can find my heat capacity in a simple way. If I just know something about my extremal black hole, pretty much what I need to do is to take the derivative of r squared. So this is very nice. It means that it depends on me moving away from the horizon of the extremal solution. Of course, we knew all along that somehow we had to have some near extremality in it, but it's kind of nice that this is the simplest way of going a little bit away, the kind of thing you learn in high school, right? Take the derivative. This is how you go a little bit away. So, you know, this is as simple as it possibly could be. This is a nice formula. I just need to find my r squared. Of course, it's still, in some ways, a little bit of a hard problem. It's not the extremal case, because I have to go a little bit away. So it's not my standard attractor. But let me remind you nonetheless how the extremal attractor works, especially the horizon attractor. How does it actually work? Well, it's often very useful to deal with extremization principles in these problems. What happens is that when you have fixed charges, you have these f squared type terms in your Lagrangian. Those f squared for fixed charges are basically something that is squared in the charges. Good. And then there are some complicated prefactors that depend on the scalar fields. So you have an effective potential for these scalars. And when I describe my attractor effect, what happens is that these scalars started somewhere at infinity, and then they have to flow to the minimum of the potential. And this is why they ultimately have to end up, in the extremal case, at the minimum of this potential. So how can I figure out what the scalars are in the extremal case? Well, the ADS2 ×S2 geometry has constant scalars. It's homogeneous. It's the same everywhere. So what are those constants? Take the potential and minimize it. And once you have the minimum of the potential, you pretty much also have, for example, the entropy. Basically, it's the square of the potential here, V, evaluated at the extremum. So the homework you have to do is to figure out what these functions are, and then you have to extremize and figure out what the scalars are. At the horizon, this is simple. This is what we do for the extremal case. And there are versions for this also when you do much more complicated things, like including higher derivative corrections and including various sorts of other stuff. So what are the results? Again, in the extremal case, well, let me introduce some notation. The results is that I find my radial function. I think about this as what is the potential at the extremum. I write that with a notation here with I4. That I4 is a nice notation for this thing because it turns out that by dimension analysis, this actually is something that is power 4 in the charges that are lengths, so therefore this is actually a quartic function, at least as far as scaling is concerned. And in many simple, important cases, it's not just something that scales like a fourth power, it's actually literally a fourth order polynomial in the charges. So that's often what the extremality gives. For example, this is a good polynomial to have in mind. It depends on the electric and magnetic charges, and that would be the correct answer for the case of, I can't even see it, but there's a paper. Is there a number on the paper? So this generating function actually is what I get out of solving my extremal attractor mechanism. And it turns out that not only should I actually compute this thing here, which is the potential at the horizon, but actually this one here, once I have this function, it actually even encodes what all my scalar fields are. I'm using, I'm sorry to say, a more fancy notation for the scalars that's using a symplectic notation that actually enhances various symmetries and putting the scalars at the same footing as the charges. But never mind, these x's here you should think about as what are the scalars at the horizon. What they are is something that is encoded in my function here. So my function I4 really tells me everything. That's the output. That's the thing I need when I need to characterize my extremal attractor. Okay, but I am not interested in the extremal attractor. I'm interested in the extremal black hole, but away from the horizon, when it's not ADS2, when it's nearly ADS2. So we need to move away. This is going to depend on what the scalars are at infinity. So let me introduce actually some notation for what the scalars are at infinity, because I'm going to encode them. I'm going to say that the scalars at infinity are obviously input data. You've given them, you've decided what they are, because it's your solution. But I'm going to tell you to put it in a form where you use this machine I just told you. I had a function that at the horizon was such that I could trade between charges and scalars back and forth. I'm saying use that function again, but use it also for infinity. Pretend to basically, instead of giving the data in your geometric form, what are my scalars, instead give it some charges kind of things. P's and Q infinities, they're not really charges, they are encoding what the scalar fields are. So I'm going to parameterize that. And the reason I parameterize that is that it happens that I can now actually give you the radial function everywhere. It was a function, in the extremal case, of just the charges. This here gives the radial dependence, is that it just becomes a linear function in the radial variable, but with coefficients that are encoding what the scalars are at infinity. So now I know how to take derivatives. The way I take derivatives is that I basically, instead of taking radial derivatives, I say, well, let me take derivatives in charge space. Because making the entire black hole bigger with bigger charges is actually equivalent, it turns out, to moving a little bit away from the horizon. So therefore, my specific heat, my symmetry breaking scale, I can get by taking the function that I already computed in the extremal case, and many hundreds of papers were written on this. So take your favorite I4, go and differentiate with respect to its arguments. And once you do that, you put coefficients in front, and those coefficients are going to be your moduli, and this is going to be the symmetry breaking scale. No need to actually study what is the entropy, let me take a limit, stuff like that. No. Extremal black holes, find the answer to the extremal black holes, and this is how you get your attractor behavior. Notice also, for example, that this is a quartic function. Once I differentiate a quartic function, I get a cubic function. So therefore, my length scale will be cubic in the charges with some coefficient that depends on my moduli. This is the answer. Of course, it's the answer for only one of the things that I have, because I promised you that there were going to be many scales. And some people are indeed saying, well, but the breaking scale, the interesting scale, is pretty much the radial derivative of r squared. Well, yeah, r squared is certainly a very good scalar field, but there were all these scalars, remember, these zi's, that after all are scalars here. And they also change as we go away from the horizon. And how do I find their change? Well, by taking my derivative in charge space. You can think about this as being something that basically says that my z's, my scalar fields, they depend exponentially as I move away from the horizon. I shouldn't move far away where they're very different from the horizon value, just by a little bit. But what is their decay constant as you go just a little bit away? Well, that's given by whatever this gives, this operator gives when I act on the horizon value. So once I figured out what the horizon value was, in the extremal case, I already get for free. How fast do they move away from the extremality? So my near extremal behavior I get for free. Let me do an example. This is the last bit of the talk. STU model, standard case, test case for these kind of things. There's an effective potential. In this case, I have 4 charges. I actually more precisely have 1 electric charge and 3 magnetic. And I have some dependence on moduli. The moduli is simple because they're not complex scalars. They're actually real scalars. They're called y instead of z here. I can interpret this geometrically as having something to do with fiber intersections and some momentum that runs along the intersection. If you study these type of models, this would be a standard setup that you would know very well. If you haven't studied those things, you are not going to learn it here. But at any rate, I get a function. It depends on the scalars. What do? I extremize over the scalars. I find some value for my scalars. The important part was in the extremal case, I get a value, horizon value for the scalars, that depends on the charges only. Very good. It did not depend, for example, on the value at infinity for my y's. Okay, very good. Then I take these values, I plug them in at the extremum. I find what is the v at the extremum, and it's something that depends only on the charges. And this is a pretty famous formula, square root of the 4 charges. So my quartic function here is going to be basically these product of these charges. What should I do now? Well, I should also go and encode the moduli at infinity as kind of charges. I use the same formula here by saying, well, this is my input, but let me trade that for some charges that look like charges. This will now give me expressions for these q's and p infinities here that depend on the y's. Good. Now I know that this directional derivative in charge space should have coefficients by some defined p's and q's that depends on the y's. So this is just a directional derivative, and this is my symmetry breaking scale, or if you will, it's the specific heat. And it depends on the moduli at infinity. And it depends on non-trivial combination of the charges. It does not depend just on this quartic thing here. No, of course not. It depends on something. You know, if this really had been something that was just like, oh, couldn't I just take this thing to the 3/4 power? Well, yeah, if all the q's and p's are equal, but if they're not, no. In fact, this expression here is pretty interesting, because you would say that, well, but what if I have a hierarchy between the charges? If I'm in the case of something that's Reister-Nordstrom, then these would pretty much be all the same. But if I'm in another case that's also interesting, where I have a hierarchy, so like say, well, this Q0 here is the smallest of all of them. Since I'm dividing basically by each of these charges here, then this thing is going to dominate when this is smallest. And that means these terms here are negligible if this happens to be the smallest. Then this really does become something that's a quartic divided by q, therefore it becomes a cubic. And not just some cubic. This product of these 3 charges here, which is what you get in the special case where there's a hierarchy between the charges, this is what otherwise is called the long string scale. It's very well known from microscopic black hole models, and the precise numbers here work out nicely and whatever. So one way to look at it is that what we're having is a generalization of the long string scale to a more general point in moduli space that doesn't necessarily assume that these charges have a hierarchy. If they have a hierarchy, we get back what we already knew. If they don't have a hierarchy, We have a new expression that's a little bit more complicated, but obviously not very complicated. This clearly is just a derivative of my quartic. So it's not that hard. So the physics of this is very good. And so the physics of this is important. These scales are things that we actually would like to know. I should also tell you what are the scales associated with the fall-off of the y's. I actually didn't even bother writing it because I can tell you what it is. This thing here has 4 terms. If instead you want what it is for the y's, you have to flip 2 signs. There are 4 pluses here. Flip 2 of them. And that's what the answer is. So basically, these 4 different terms, I should actually think about separately as being my 4 scales. So the 4 scales in my system is, perhaps this one is the most important, I don't know, but in general, it's all 4 of them. And the reason that they thought perhaps there was universality, I can now explain, is because they didn't consider that they could be different, these 4. You know, if they're the same, there's only 1 scale. But well, they're not. There are many different directions in your charge space where you can take derivatives. So there you go. I'm going to summarize. This near ADS, near CFT holography just describes the near horizon region of these nearly extremal black holes. I have emphasized just a single aspect of that construction, namely, what about the scales? The scales depend now on scalar fields, but the scalar fields and their dependence on the nearness and the is particularly simple. In fact, if I've studied this in the extremal case, which in many cases we have, then you can get the result for the near extremal case simply by differentiating with respect to the parameters of the near extremal horizon, of the extremal, of the charges. And that's something that you already know. You know the entropy as function of charges. Go differentiate to your heart's content, and that will give you the scale with which these things will fall off as you go slightly off extremality. Thanks for your attention.
Okay, thank you. Any questions? Yes.
If I had to make a wild guess, is capital L the scale that multiplies the Schwarzschild?
The
Schwarzschild term.
Yes, of course.
Okay, just.
Yep.
So it's still.
No, but there's not. So you see, you're now saying, oh yeah, gravity is important. Well, I agree with you that there is a dimension 2 operator corresponding to gravity in the dual theory. It's an irrelevant operator, 2 being more than 1. However, there's also a dimension 2 operator for each of my currents. Because if I put in an extra gauge field, actually that will have a dual operator, and that dual operator also has dimension 2. So I have as many dimension 2 operators, and I have no reason to believe that one or the other should be more important. I know, you think they were dimension 3, but they're not, they're dimension 2.
No, I didn't think that they were dimension 3.
So there are as many, so in the dual theory, which I haven't developed, I'm saying that I break the symmetry, but I have a choice with how I break the symmetry. And I have no particular reason to think that these things should be different, that one should be more important than the other. Well, maybe you have a reason, but I...
Any other urgent question?
There was one over there, but I...
Yes. Okay, let's thank Finn, and we can continue the discussion over coffee.
I couldn't see your times at all. I could only